Okay. This is from, I believe, spring 2022 or fall. Hold on, I have to find out. Spring 2022. All right, so we're going to start with the formal charges on the oxygens, oxygen 1 and oxygen 2. Oxygen 1, so I'm going to call that O1, has 6 valence electrons, has 6 lone pair electrons, and 1 bond. So that's going to be -1. Oxygen 2 also has 6 valence electrons, 4 lone pairs, 2 bonds, that's 0. So when I'm looking for a -1 and a 0. Oxygen, so I can already say oxygen 1 should not be +1. It has to be B. What is the hybridization of the central carbon? This is the central carbon. That central carbon is only bound to 2 things. That makes it sp. What best describes the configuration on the following compound? I'm looking, my Br and my largest group here are on the same side. That makes it Z. Which of the following is not a conjugate acid-base pair? If I'm looking, the only one that does not have a proton in one and then not in the other is this, because I have different numbers of nitrogen. Different numbers of oxygen. That's not part of being an acid-base pair. Okay. Name the compound below. First, get rid of the things I know it can't be. This is 1, 2. So 1, 3 it can't be. Oh, sorry, 1, 3, sorry. Whoops, that. It's 1, 3. 1, 2, 3. So 1, 2 is wrong. 1, 2, and 1, 4 are wrong. Question, is it cis or trans? It's cis. Answer C. What best describes the structure above? So if I look at it as just that regular picture, boom, whoops. I'm going to do it as a dash and a dash. This is a meso compound. So it has 2 chiral centers, but it's not a chiral compound. So A is incorrect. Has chiral centers, so B is incorrect. And it's got to be C, meso achiral. You cannot be meso if you have no chiral centers. You're just achiral. Which of the following is non-polar, has a 0 dipole moment? So let's look at where things are being pulled. This is being pulled 2 equal and opposite directions. On B, we have 3 things being pulled, and net we're going up. C, net we're going up. We only have 1 thing being pulled in D. And then in E, we're clearly being pulled toward the side. Therefore, A is the only one that doesn't have things being pulled. All right. Which line angle drawing best represents the Newman picture shown? So now, if I'm looking, I see my CL is up. So I'm going to start with those that have the CL just pointing straight up. So that gives me C and B. Yes. So now, for C and B, my CL is to the left, which means when I rotate that Cl around, my methyl group's pointing at me and my hydrogen's pointing behind me. So clearly it can't be C. So the Cl looks correct, this looks correct, this looks correct. My hydrogen's pointing down. My Cl on the other side, just like this methyl, is coming at me. And the CH3 is the CH3 in the back is going back, just like that hydrogen. So it's B. Okay, what's the relationship between the following two compounds? Let's eliminate what it can't be. There's only one chiral center, so it cannot be diastereomers. They both have the same chemical formula and there's only one carbon. It cannot be constitutional. So they are either the same or enantiomers. 1, 2, 3. This is S. 1, 2, 3. This is also S. They are identical. Again, what is the relationship between the two? There's only one chiral center, so they cannot be diastereomers. They're attached the same way, so they cannot be structural. They are either identical or enantiomers. 1, 2, 3. This is R. 1, 2, 3. This is also R, but because the hydrogen's coming at me, this is S. They are enantiomers. If I look at number 11, if I just rotate this first one, this one, so that they face each other, you will see that this CH3, OH, these two are mirror images of each other, which means they can't be diastereomers and they cannot be constitutional. They're either enantiomers or the same. So I look and see, do they have a plane of symmetry? They don't. So I say that they are enantiomers. So that's A. 12. What is the relationship between the following compounds? So I look and I see that they're attached the same way. They have the same chemical formula. I look at the chiral centers. This and this are the same. This and this were inverted. So because one stereocenter is the same, the other is inverted, they have to be diastereomers. I look at these now. Same exact thing. I see that they're the same. I see that this and this are the same. Oh, sorry, this and this are the opposite, sorry. So I switched these two. These two are both switched. So now I know that they are either enantiomers or the same. They cannot be conformational, they cannot be diastereomers, or constitutional. So now I rotate around, Boom, boom, boom. So here's my Cl. My hydrogen's up. Once I rotate around, my hydrogen goes back and my chlorine comes forward. So they are not mirror images, so they are not superimposable mirror images. They don't have a plane of symmetry. They are enantiomers. All right, now we get to 14. Also similar looking. Do they have the same chemical formula? 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5 carbons. 1, 2, 3 chlorines. 1, 2, 3 chlorines. They both have the same chemical formula because there's 0 degree saturation. So they cannot have different formulas. Then I look and I see this has an HCl, this has an HCl, this has an HCl. And then I look, this has 2 Cl's and this has 2 H's. They're not attached the same way. Therefore, they have to be constitutional isomers. What is the relationship between the compounds below? This is cis. Whoops. This first one is cis. This one is trans. Therefore, they're configurational or diastereomers. Okay, 1 bromopropane. I was so nice. And I want a Newman projection. Whoop. So if I'm looking at a methyl, all of these are hydrogens. Hydrogen, hydrogen, hydrogen. The bromine is going to be here, Br. A methyl, CH3, and a hydrogen. Just having it staggered. Which of the following cannot exist? The only one that cannot exist is F. Do not have more than 4 bonds to carbon. Oh Lord. Do not allow more than 4 bonds to carbon. Otherwise. All right. So now we're going to draw the enantiomer, and I'm going to label it E. So all I'm going to do, bump, bump, 1, 2, 0, oxygen, 1, 2, oxygen. So here's the OH, here's your H. Here's your OH, here's your H. That's your enantiomer. The diastereomer, I'm only changing one thing. So I'm going to keep this H and this OH where they are. Double bond 0, double bond oxygen. Boom. I'm going to move this one OH and H. Double bond oxygen. Now if I look at my diastereomer has a plane of symmetry. Therefore, this one would be meso. Most stable chair conformation. All I know is that this has to be equatorial. So I'm going to make my chair. Whoops. Boom, boom, boom. And I'm going to make it so that my T-butyl is equatorial and that my 2 methyls go up and down. That's it. That's all you have to do for that one. And then identify the most acidic hydrogen. The most acidic hydrogen is going to be the one on the carboxylic acid. And write down the reaction with sodium hydroxide. So it's going to be oxygen, double bond O, and because I am running a little bit short on time, I'm just going to write it as R. Even though that's not RRRS, it's just showing the whole molecule. Identify all of the chiral centers. So this is a chiral center. This is a chiral center. Using wedges and dashes represent the stereoisomers in S configuration. 1, 2, 3. It is naturally going in S. I don't want to have the hydrogen coming out, so this is a wedge. 1, 2, 3. This is also a wedge. One structure of a cation is shown. Provide two other structures. Oh. That here, yep. Provide two other structures. So I go here, and that gives me N H, and now there's a double bond here and a double bond here, and my plus is on the nitrogen. And then I can also do one where this comes in to alleviate. So here I have NH2, a double bond here, and a plus on this carbon. Do I have anything else on here? That's it. Okay, that's it for this one.